In this video, we're going to be solving some similar figures. That means that we're going to be finding some unknown measurements between two similar figures. In order to do that, we need to understand this concept of a scale factor. And a scale factor is most simply just how much bigger or how much smaller one shape is compared to another. But more specifically, a scale factor is really a ratio that we can write when we compare two corresponding measurements in these similar figures. So we can compare two corresponding sides, and we can simplify that ratio. But we can also compare perimeters or areas of similar figures, and we should get the exact same scale factor. So let's take a look at this example. If I'm told that these two shapes are similar, I mean, we could prove it, but I'm just going to tell you that they're similar. Then if we compare two corresponding parts and set it up as a ratio, we should be able to get this scale factor, or how much bigger or how much smaller one shape is compared to the other. So if I compare the corresponding left sides, I can set up a ratio saying 10 to 20. If I reduce that, then I get a 1 to 2 ratio, and that's my scale factor. So this smaller triangle is a half as big as this bigger triangle. Now I could flip that. I can compare the big triangle to the small triangle, and then I would set up a ratio saying 20 to 10, and I would get a scale factor of 2 to 1, saying that this bigger triangle is 2 times bigger than the smaller one. It doesn't matter which one you do, as long as when you are setting up your ratios, you keep the same comparison, meaning if you're comparing left to right, you keep comparing the left pieces to the right figure's pieces. All right, so we can do that with any of these corresponding sides, and we should get the same scale factor. So if I compare the two right sides, I would say 6 to 12, and that reduces to a 1 to 2, so our scale factor holds up. And lastly, at the bottom, I can compare 7 to 14, and I would still get an equivalent ratio 1 to 2. So my scale factor is indeed 1 to 2. I can do one more thing just to show you that we can actually compare the perimeters of our similar figures here, and we should get the same scale factor. So if I add up all of the lengths in my smaller triangle, I get 23. If I add up all the lengths in my bigger triangle here, I get 46. And if I compare that as a ratio, it reduces and holds that scale factor ratio to be true, 1 to 2. So let's keep practicing that concept. We're going to find the scale factor, and we're going to use it now to solve for some unknown measures in these two similar figures. So being told that these two figures are similar, we're going to be able to solve for this unknown length here, this unknown length here, and this unknown angle measurement here. So the first thing we want to determine is the scale factor. How do these two figures compare to each other? I'm going to compare the left shape to the right shape, and I'm going to try and find some corresponding sides here. So if you're confused by the picture or the diagram, and you're given a similarity statement, you can actually use that statement to determine corresponding parts. So corresponding parts are always in the same order in the name. So if I want to compare MN, then I would compare it to what corresponds over here, RS. So I know that 18 can compare to 30. So if I set that up as a ratio and reduce, I get a 3 to 5 ratio, and that is my scale factor. So we can use that scale factor now, and we can use proportions to solve for some unknown measurements. Remember that side lengths are going to be in proportion, so we should be able to set up some equal ratios and find an unknown value in that proportion. So you're always going to start off by using that scale factor ratio, 3 to 5. That's how these two shapes compare, and we want to make sure that we set up another ratio of corresponding parts so that we can solve for an unknown value. So if I want to solve for x, I need to figure out what corresponds with side length NP, or segment NP. So looking in the name, I look at the same spot in the other shape's name, and ST is going to correspond. So I know that x corresponds with 25. So if I set that up as a ratio, making sure that I set up the same comparison, I'm comparing the left shape to the right shape, then we can diagonally multiply or cross multiply and solve for that unknown value. So diagonally multiplying, we get 5x equals 75. If I divide both sides by 5, I get my side length is 15. We can do the same thing to solve for y. Start with that scale factor ratio and set it equal to two more corresponding parts. We want to solve for y, so what corresponds with tu? Well, looking in the name, pq corresponds, so 15 to y would be my ratio. I could diagonally multiply and get 3y equals 75, and then divide both sides by 3 to get the side length value of 25. By this time, we should know that similar figures have congruent corresponding angles. So if I could figure out what corresponds with angle M, I could solve for the measurement of Z. So looking at the name, M corresponds with R. So angle M must be the same measurement as angle R. So angle M must measure 115 degrees. Let's practice again. This time just a different example. And this time we're going to be solving some proportions so that these shapes are similar. First thing we want to do is set up a scale factor involving two corresponding parts that we know. So sometimes you got to look for them. It looks like we know the right length of the tiny triangle, and we do know the right length of the big triangle. We just got to combine these two values, 9 and 3. So if I compare the small triangle to the big triangle's lengths, I can set up a ratio saying 3 to 12, and then reduce that to get my scale factor of a 1 to 4. So this tiny triangle is a fourth as big as the bigger one, or the bigger one is 4 times bigger than the smaller one. So I'm going to keep that small to big comparison going in my proportions. So I'm going to always start with my scale factor. And if I want to solve for y, let's do y first because it's a little less tricky. Then I want to figure out what corresponds with TR. I can look on the left side of the big triangle here. If I want to set up my ratio comparing the small to the big, I would say y to 12. And then we can diagonally multiply and get 4y equals 12. Divide both sides by 4 to get the side length of 3. Now to solve for x, it's a little bit trickier, but we could do it. I know that the big triangle's bottom length is 15 plus x. And the bottom length of the small triangle is just x. So if I set up a ratio comparing the small triangle to the big triangle, that would be x to 15 plus x. So the small triangle's length compared to the big triangle's length. And we're going to set that equal to our scale factor every time. Diagonally multiply. Be careful if you're multiplying an expression with multiple terms here. If this value was anything other than 1, you would need to distribute that. But here, 1 times anything is just itself. So we got 15 plus x equals 4x. We could subtract 1x from both sides and get 15 equals 3x, and then divide both sides by 3 to get our x value of 5. So now we know that this side length is 5. We could figure out the total side length down here for the big triangle. That would be 5 plus 15 or 20. But we weren't asked that. So there's that problem. One more example, or a couple more examples. This time we're going to practice using the perimeter to try and help us find some unknown values. So if we're told that both of these trapezoids are similar, or quadrilaterals, and we know that the perimeter of the small trapezoid is 12, and we're told that the perimeter of the big trapezoid is 16, we're also told some other values. If you're just told a lot of values in a description, it's always nice to label your picture or put those values in your picture so you can visualize everything a little bit easier. So we're given the AB length here, we're given the CD length over here, and the WZ length. And we want to solve for WX. Well, it seems kind of difficult, but let's take it a step at a time. What two corresponding values do we know? Well, if you're looking at your picture after you filled in these values, you can see that we don't really have any corresponding side lengths. But we are told what the two perimeters are, so we can actually use those corresponding perimeters to find our scale factor. So if I compare the small trapezoid to the big trapezoid using a ratio of perimeters, I would set up a 12 to 16 ratio and reduce that by 4, and I could come up with my simplified scale factor of 3 to 4. Now we can use that to find other corresponding lengths. So if I want to solve for WX, WX in the name corresponds with AB. We're told the length of AB, so we can solve for WX. We're going to use our scale factor as our first ratio. I'm going to substitute 6 for AB, and we can diagonally multiply and divide both sides by 3 to get the length of WX is 8. So I'm running out of time in this video. I'll do this last example in another video.